Now we're going to have a look at buoyancy and why things float. We all know that if something's lighter than water, it'll float on top of the water. And we all saw in school that Archimedes, with his eureka moment, told us that the force of buoyancy was going to be equal to the weight of water displaced. So let's unpack that a little bit. The weight of water displaced, well, if we look at the amount of this body here that's actually below the water line, then we can find that there's a volume of water that's been displaced. So if we are unpacking, that'll be the integral over the volume. Well, let's simplify. Let's start just by multiplying by the volume. It'll be density times gravity times the total volume of water displaced. And in this case, make sure that you notice that this density, this is going to be the density of the fluid that's being displaced. So in this case, if it's something floating in the water, this is the density of the water. Now, if we wanted to figure out what that was, we could do an integral over the entire volume, this whole region here, of rho g times dv. Or, if we take rho and g as constants, that's just the integral over the volume of the incremental volume. So that's not telling us too much that we don't already know. Let's look at this in a little more detail. If we put a coordinate system on here, and we'll call the vertical dimension z, then we've got x and y, defining the planform projection. This is the horizontal plane, is the xy plane. If we've got our body sitting here, and it's underwater to some extent, then everywhere over this body we can define what the height is, the distance that this surface is under the water. So h is going to be some function of x and y. And in the vertical forces, we would have to integrate over the entire planform area. Now, horizontal forces, well, let's see where the pressure's acting. There's pressure forces acting upwards on that flat bottom. There's a pressure force over here. It's a little smaller magnitude of pressure because we're not as far under the water. And we've got pressure forces acting all the way around this body. And the deeper under the water we are, the higher the pressure is. Now, if we consider horizontal forces only the horizontal components, then the force pushing this way on this side and the force pushing that way on that side, they're all going to cancel out. However, the forces pushing upwards vertically don't have any corresponding forces pushing downwards if we work in gauge pressure. So the horizontal components, they cancel out. Vertical components, we will have to integrate over the projected area in the horizontal plane. So each little elemental area dA in the horizontal planform plane. And our h is a function of x and y, and it's what defines the shape of this floating body. So our force due to buoyancy is going to be equal to the integral over that projected area, the area under the body here, of rho g h. That's going to be the pressure at any one of these points, defined by h of x and y, how far under the water we are, times the projected area, this area in the horizontal planform plane. Or just equal to integral over the area of p dA. So this buoyancy force is really a pressure force. It's the same kind of pressure force that we've been calculating all over the place. And whether we start from Archimedes' principle or start from integrating the pressure force, we'll wind up back here. And let's follow this one through from Archimedes. There's the buoyancy force. It's the integral over the volume of rho g dv, or just the integral the integral over the volume dv times rho g. That'll be equal to, well, rho g times dv. Well, if we looked at a region in here, then the elemental volume that we're looking at will be h high and dA, planform area, in projected area in the planform. So that would be integral over the area HdA, or since rho g times h is the pressure locally, that'll be equal to the integral over the area, P dA. And those are exactly the same thing, whether we start from thinking about what's going on with Archimedes, or whether we start from thinking about a distributed pressure force acting over an area which is supporting this thing that's floating in the water. Either approach is valid. Either approach will tell you what the answer is, but I like this approach better in terms of understanding pressure forces and how they're distributed over the body. And it's going to tell us more information later on if we keep thinking about these distributed forces in terms of the way the body here floats and where that force is more concentrated. Next, we'll move on and we'll look at what happens when we have submerged bodies.